All right, this is section 6, which is related rates. So related rates are a use of the chain rule to find rates of change of two or more related variables that are changing with respect to time. Normally we've been taking the derivative with respect to x. Now we're taking a derivative with respect to this new variable, time. So for example, the volume of a conical tank that is draining. The volume of a cone is pi over 3 r squared h. So when we take the derivative, we have the derivative of v, which is dv dt. We're going to leave the pi over 3 out front and deal with the rest of it. So we do the derivative of r squared, which is 2r. Oops, I lied. The derivative of h is dh dt times r squared unchanged, plus the derivative of r squared, which is 2r dr dt, times h unchanged. That's how we get our new derivatives with respect to time. So in my question here, in a conical tank, the height of the water is changing at negative 0.2 feet per minute, and the radius is changing at negative 0.1 feet per minute. What is the rate of change of the volume when r equals 1 foot and h equals 2? Well, we just had the formula. We just plug things in. The height is changing, so that's dh dt is negative 0.2. The radius is changing, so that's dr dt at negative 0.1. We know r is 1, we know h is 2, we just plug these values in. So dv dt equals pi over 3 times, our formula just said r squared, so 1 squared, times dh dt, which is negative 0.2, plus 2 times r, which is 1, times h, which is 2, times dr dt, which is negative 0.1. We just type this all into the calculator and we will know how quickly our volume is changing. 1 squared times negative 0.2 plus 2 times 1 times 2 times negative 0.1. This whole thing makes negative 0.6. Divide by 3. I get dv dt equals negative pi over 5, which is approximately negative 0.628. Our volume is cubic feet per minute. The derivative will be a rate per something. So does dv dt depend on the values of r and h? The answer is yes. Depending on the radius and the height at the time, the volume is changing at a different rate. It's changing faster or slower depending on our volume, or our height and our radius. So given that y equals x squared plus 3, find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Notice that this is asking for derivatives with respect to t, which is why we need to use implicit differentiation. So we implicitly derive this function. The derivative of y would be dy dt equals the derivative of x squared is 2x dx dt plus the derivative of 3 is 0. So we know x is 1, we know dx dt is 2, plug those numbers in. Dy dt equals 2 times x, which is 1, times dx dt, which is 2. So dy dt in this case is 4. No units given, that's our answer. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Remember, concentric circles are just circles that share a center. So it kind of goes whoop, 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 as it goes when you drop a pebble in a pond. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So that's dr dt. Dr dt is 1. When the radius is 4 feet, so when r equals 4, at what rate is the total area changing? I want to know dA dt. Well, what relates the area and the radius? The area formula. Area equals pi r squared. So now we take our derivative. The derivative of A is dA dt equals 2 pi r dr dt. And then we just plug in what we know. We know r, we know dr dt. The derivative of A with respect to t equals 2 times pi times 4 times 1, which means that the derivative of the area with respect to time is 8 pi, which is approximately 25.133. Area is measured in square feet per second. Look back to your problem to determine the label. All right, some guidelines for your related rate problems. Identify everything that was given and everything you need to determine, and make a sketch if it'll help. Write an equation involving the variables whose rates of change either are given or are to be determined. Then use the chain rule to implicitly differentiate both sides with respect to time. Finally, after completing step 3, substitute into the resulting equation all known values for the variables and the rates of change. Then solve for the required rate of change. You have to do step 3 before step 4, otherwise you'll get it wrong. You have to take the derivative of everything before you plug anything in. You have to. Otherwise there won't be anything to take a derivative of. So, some examples of times that we would use are related rates. Velocity of a car after traveling for 1 hour is 50 miles per hour. We have a distance traveled. We have a rate of change. We have time. That kind of stuff. Let's dive into our next example. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So air going in, that is a change in volume. So that is dV dt is 4.5. Find the rate of change of the radius when the radius is 2, so that's r equals 2. We are looking for dr dt. So what relates the radius to the volume? Well, volume of a sphere is 4/3 pi r cubed. So now we take the derivative. dV dt equals 4/3 times pi times, bring down the 3, r squared dr dt. Let's clean this up just a little bit before I start plugging values in. dV dt equals, well, the 3's cancel here, leaving me 4 pi r squared dr dt. And now I'll plug in dV dt and r because I know those values. 4.5 equals 4 pi times 2 squared dr dt. I'm solving for dr dt. Multiply out this right side, I get 4.5 equals 16 pi dr dt, and divide by 16 pi. You could leave it as 4.5 over 16 pi, or you can turn it into a decimal. Make sure that when you turn it into a decimal, you take 4.5 divided by, and then put parentheses around your 16 pi. Because otherwise your calculator will divide by 16 and then multiply by pi. So we get 0.0895. And I'm going to go 4 decimal places just because that's a 5. Our radius is in feet per minute. Feet per minute. All right, next one. An airplane is flying on a flight path that will take it directly over a radar tracking station. The distance s is decreasing at a rate of 400 miles per hour, so ds dt is negative 400 because it's decreasing. When s equals 10, cool. What is the speed of the plane? Now this picture will help. Our plane is 6 miles in the air. X is going to represent its horizontal distance. S is its distance actually from the station. Well, what relates these sides together? Pythagorean theorem. 6 squared plus x squared equals s squared. Now we can take our derivative. The derivative of 6 squared is 0. The derivative of x squared is 2x dx dt equals the derivative of s squared is 2s ds dt. We know s. 2 times s is 10. We know ds dt is negative 400. We don't know dx dt, that's what we're looking for. We know the 2, but what is x? We can't solve for 2 variables at once. But we can take a little sidebar here and say, okay, well when s is 10, I can solve for x. 6 squared plus x squared equals 10 squared. Go back to the original equation we wrote. That's how we can solve for x. So 36 plus x squared equals 100, which means x squared equals 64, which means x must be 8 because the distance can't be negative. So I'll plug in that 8. So 16 dx dt equals negative 8,000. Divide by 16. Dx dt is negative 500. But that's not the answer. This question asked for the speed. Speed is never given as a negative value. Speed is only given positive. And we are in miles per hour. That plane is moving 500 miles per hour. The negative is a velocity. It tells us direction involved also. It tells us it's getting closer at a rate of 500 miles per hour. But speed, always positive. All right, and we have a television camera. This is going to be our last example. It's at ground level, and it's filming the liftoff of a rocket that is rising vertically according to the position equation s equals 50t squared, where s is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. We're going to find the rate of change of the angle of elevation of the camera shown at 10 seconds after liftoff. So given our picture here, we are going up s, and I care about the rate of change of theta, the angle. So let's first relate s and theta. Well, if I know this 2,000, I know opposite over adjacent. I know the tangent of theta equals s over 2,000. So I can take the derivative. Derivative of tangent is secant squared d theta dt equals, this is 1 over 2,000 times the derivative of s, which would be ds dt. But this gave us an equation for s. So I can find ds dt from that. Let's go right here. ds dt is equal to the derivative of this, which is 100t. So I'm going to plug that in right here. Secant squared of theta, d theta dt, equals 1 over 2,000 times 100t. Now let's plug in what we know. We know what t is. T is 10 seconds. But do we know theta? The answer is not yet, but we can figure it out. If I know that the tangent of theta equals s over 2,000, well, I can find s because s is 50t squared, 50 times 10 squared. To solve for tangent, I use arctangent. So in my calculator, I will take secant tangent of 50 times 10 squared over 2,000. Make sure that I am in radians because calculus is always in radians. There's my answer, 1.1902 blah, 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 blah. When we plug that in, try your best to not round it. So I want secant squared of 1.190-ish d theta dt equals 1 over 2,000 times 100, t is 10. So to type all this in, I'm going to do this side by hand. I get 1,000 over 2,000, I get 1/2. All right, d theta dt. To get secant squared of 1.190. Now I can't do secant in my calculator, but I can do 1 divided by cosine. Use my second answer key so that I don't have to type in that long decimal. But it's squared, so I get that number and I square it. 7.25. So to solve, I divide by 7.25. I have 1/2 divided by 7.25. d theta dt is equal to 0.0689, so 9 radians per, what's our time in seconds? Radians per second.